Assalamu alaikum. I hope we can now start. So, was anyone able to derive the Planck's formula? Why? Did anyone try it? So that's why you weren't able to derive it. Could you please stand up, gentlemen, and tell me where did we leave the last lecture and where are we standing now? आप बता सकते हैं ब्लैक स्पेस इधर आए इधर देखिए दिस कोर्स आई एम ओनली अ टीचर and I can only in 1 hour and 15 minutes I can only give you an overview and motivate you to study on your own. I'm not going to spoon feed you with information and you have to read things on your own. And if I request you to derive a formula or do some work on your own in between two lectures, it's your responsibility to follow the course material with me, and it's not my responsibility to hammer in information into your head. So you really have to follow me. You really have to act upon my requests. That is, go home, study, and do what I ask you to do. That's the only way we can learn this course. My responsibility is only 50%, the rest is yours. You have to work on your own. So could anyone tell me in a very precise way where we stand now and where did we finish our last lecture? Ji.
Do I have to stand up?
Huh?
So basically we finished up how Planck actually arrived at his formula for the quantization of energy and how that explained the black body radiation better than the other model.
Alright, that's good. So we really have these spectral energy density curves and we're going to spend not more than 10 minutes on this. So we have a frequency here and we have an energy density. And we saw that the classical formula, which is the Rayleigh-Jeans formula, worked well for the low frequency limit for black body radiation. It works very well for the low frequency or the long wavelength limit. But it breaks down for the high frequency regime. And Planck tried to circumvent this problem. He tried to overcome this problem by proposing that inside the cavity there is radiation. And inside the walls of the cavity there are atoms, and atoms oscillate in a quantized fashion. That is, their energy E is quantized or discrete and it varies as NHF. So based on this quantization he was able to derive an average energy, which is U in our notation. So the atoms of the walls of the oscillator are quantized. They are harmonic oscillators. They are like masses attached to a spring. They have an energy 0, or they could have an energy HF, or they could have an energy 2HF, PHF, and so on. So these are the possible energies of the oscillators inside the walls of the cavity. And the average energy can be obtained not by an integral but by a discrete sum, because now the energies are quantized, they are discrete. So we cannot integrate, rather we have to find the discrete sum of energy. And the energies are now NHF multiplied by the probability multiplied by the probability that an atom can have this much energy, and the probability is exponent minus NHF over kBT. So this is the Maxwell-Boltzmann. This probability comes from the Maxwell-Boltzmann distribution. The only difference, the only real leap of imagination of Planck is that the energies are quantized. So instead of having a continuous energy here, the energy is now a discrete value, NHF, where n is an integer. So this is Maxwell-Boltzmann formula for the probability that a system has a certain energy. The only difference is that the energy is now NHF. It's quantized. The energy can be 0, HF, 2HF, 3HF, and so on. And this sum has to be taken over all values of n, ranging from 0 to infinity. And you also have to normalize. And this is the discrete sum I asked you to try out as a homework. Okay? Now I'm not going to do it in the class, and I can ask this in the exam as well. But you are required to perform this calculation. And when you perform this calculation, it turns out that the average energy equals HF divided by exponent HF over kBt minus 1. So this is like a geometric progression, an infinite geometric progression. You can put HF over kBt equals to x and solve this as a geometric progression. And when you solve this as a geometric series, you will arrive at this result. So this is something which is do it yourself. It's easy. So this is now the average energy given by Planck. And the leap of imagination from Planck is that the energies are quantized. The energies of the atoms making up the walls of the cavity are quantized. And see how this contrasts with the energy, the average energy proposed by Rayleigh engines. And what was that energy? वो energy क्या थी? Average energy kBt. Okay? This had no frequency dependence, but now this has a particular frequency dependence. So this is the Planck's formula. This is the Planck's formula. And as you can see, this energy depends upon both the temperature and the frequency. This average energy. Now what happens to this energy in the limit of small frequencies? If you have this average energy and you take the limit of small frequencies, what happens? What do you get? Can anyone try out the calculation? It's very easy. I'm going to ask you. Try it out. What happens when the frequency is small? What happens to the exponent of a small number? What is the exponent of a small number? 1 plus HF kBt plus higher orders. You will get something equal to kBt. So this is simple calculation you should be able to perform. This has nothing to do with modern physics. It's a basic, simple mathematical, a one-liner. So this number, in the limit of small frequencies, nothing happens to the numerator. This exponent can be expanded as hf 1 plus hf over kBt plus hf over kBt, higher powers, and so on, minus 1. So the 1 cancels out. These higher powers are so small that we can neglect them, and what we are left with is kBt. So this is exactly the classical result. So the Planck's formula asymptotes or gives the classical result in the limit of the small frequency. So that's a motivation, and that gives us confidence that the Planck's formula is correct, because in the classical limit it reproduces the Rayleigh-Jeans formula. And at high frequencies, what happens at high frequencies? In the limit that the frequency is large, what happens to you? It approach at f goes to infinity, you approach 0. But for f large, you have hf. This term is much larger than 1, so you can ignore the 1. You get exponent minus hf over kBt. So this is a decaying exponential. And this is what I mentioned in the previous lecture, that Planck wanted to come up with a formula which gives the correct classical result in the limit of the low frequency, but in the high frequency it decreases the spectral energy density and avoids the ultraviolet catastrophe. And the only saying only is an understatement, but the contribution of Planck was that he came up with the idea of quantization, which is at the heart of quantum physics. So now if we use the Planck's formula for the spectral energy density, which is simply the density of modes that we have already calculated, which is 8 pi f squared over c cube, and we multiply it with the average energy of the mode introduced by Planck, which is the quantized energy. If we use this corrected formula and we plot it, we will exactly reproduce the experimental curve. So we have fit the experimental curve to its proper fitting function. And the fitting function, the fundamental property of the fitting function is that the energy is quantized. So that is how the idea of quantum mechanics was born. 1896, Planck, working on the experimental work which preceded him for a couple of centuries, he came up with this bright idea that the energy of the atoms making up the walls of the cavity must be quantized. So this is the singular achievement of Planck, of Max Planck. And this is where the whole idea of quantum mechanics and quantization and discrete energy levels was born. ठीक है? ये quantum mechanics का आगाज है. And since then it never stopped. It has never stopped. The progress in quantum mechanics keeps on happening each passing day. But it's important to know the roots of the area. And the roots lie in Planck's seminal work and in his bright idea that the energies must be quantized. Okay, any questions up to so far? देखो जब limit approaches infinity है ना, this is also increasing with the power of 1, but this is an exponentially decaying function. This is decreasing to 0 much more rapidly than this is increasing. Okay? So the scaling factor is exponential, but this is linear. So this factor dominates and the product goes to zero. यही हमने बात की थी ना कि Planck wanted to come up with an average energy which gives the correct classical result at low energies, at low frequencies, and it goes to zero so that we can avoid the ultraviolet catastrophe and the energy can remain finite and bounded. So the ultraviolet catastrophe problem has now been solved. So now what we really have, let's take a closer look at quantization. And remember, this is a very important concept, so we really need to understand it well. So we have a harmonic oscillator. An atom is like a harmonic oscillator and it has a certain energy. And according to quantum theory, the energy is quantized. It's NHF. So when we depict this system, if we plot the energies on this axis, we say that we have energy levels. That the energy of this system can be quantized. So we have a ground level corresponding to n equals 0 with zero energy. But I am going to correct this statement later. But we have a ground state energy for n equals 0. Then we have an energy level n equals 1. At this level the energy is HF. Then another level n equals 2. Energy is 2HF. N equals 3. Energy is 3HF. And so on. And these are equally spaced levels for a harmonic oscillator. So the oscillator can only have an energy 0 or HF or 2HF or 3HF. It cannot have an energy in between. ठीक है, हम किसी बाग में जाएं, आपने स्लाइड भी ली होगी, बच्चे खेलते हुए भी देखे होंगे. तो जब स्टेप्स के ऊपर आप चढ़ते हैं, when you walk up the steps, you can only be on a step. You cannot hang in between. So the upward ascent is quantized, it's discrete. But when you come down, you enter the classical world. You can have a height that varies from the maximum height to 0, and it can vary continuously. But going upwards, you can only take those discrete steps. Okay? You cannot hang in a balance in between the two steps. So the upward motion is quantized, whereas the downward roll is analog or it's continuous. But quantum mechanics says that even the downward roll has to be quantized. Now the question is, if the downward roll is classical, it means it's non-quantum. But I've already said that quantum mechanics is how nature works. So how do we explain this discrepancy? Suppose we have a pendulum. This pendulum has a fixed length, L. What's the frequency, the natural frequency of this pendulum? क्या है frequency? यही है ना? So this is the natural frequency of the pendulum. Now you perturb the pendulum and it starts oscillating. And if you are in vacuum, there is no friction, it will oscillate forever. It will keep its fixed frequency f. And the energy will remain fixed. The energy of this pendulum will remain fixed. And what is the energy of the pendulum? Px squared m is proportional to f squared, correct? The energy will be proportional to omega squared or f squared. Okay? Potential energy half kx squared, hai na? K is m omega naught squared. So the energy is proportional to f squared. so its energy will remain constant. But if this pendulum is in vacuum, it's not in vacuum, it is damped with time. That is, the oscillations keep on decreasing with time. So the energy keeps on decreasing with time. So if you look at the classical world, our classical concept, a non-quantum concept, and if we plot t versus time, the energy of this damped pendulum, can you tell me what this plot will look like? Can you draw on your notebook what the plot will look like? एनर्जी मतलब डैम्प हो रहा है पेंडुलम. ठीक है, this is a basic physics question. Mechanics पढ़ने के बाद you should be able to answer this question. Just think intuitively, how should the energy decrease, or should it go up? इस तरह तो नहीं होगा. एनर्जी कम हो रही है, फिर बढ़ रही है, डैम्पिंग हो रही है, फ्रिक्शन हो रही है. ये एनर्जी कम होने के बाद फिर बढ़ गई, वो क्यों? Total energy of a pendulum which is not damped remains constant. It's being jumping between kinetic and potential energy. But for a damped pendulum, the total energy keeps on decreasing. So it's decreasing like an exponent. Everything, natural systems behave exponentially. So it decays like an exponent. Now when it decays, its frequency also decreases. Is this decay continuous? Yes. It's taking up all possible energy values between its maximum and zero till it finally comes to rest. But this violates the quantum thinking, but it's intuitive, and this is really what we observe. Okay? So the frequency is also taking up all possible values. But if this weren't a pendulum, if this were a single atom or a microscopic system, things would be different. अगर आप एक अखबार का कागज लें या आप ये सफ़ा देखें, and you're looking at this paper from a distance, you will not be able to decipher or look at the original letters that I've written on this paper. ठीक है, आपको original letters नजर नहीं आएंगे. What you will see from a distance is a blob or a smeared out picture, a continuous picture of black ink on a white paper. That is what you will be able to see. But if you look closely and if you bring the paper closer to your eyes, the individual lettering will start appearing. It will start making its impact. You will be able to tell that this is A, this is Y, this is C, this is D. The individual letters will come out as discrete units, as quantum units. So a classical system is a big macroscopic system. But if you probe it deeper, go closer and closer to it, that is, you look at the level of atoms, you will be able to see that everything is quantized. And if in the quantum picture, this energy does not go down continuously, rather this plot is really made up of a staircase. And the only point, the only reason why we do not observe this staircase is that the height of each stair, which is hf, is extremely small as compared to the total energy. That is, delta hf the height of the stair is extremely small. H is an extremely small number. H is really 6.627 into 10 raised to the power minus 34 joules second. So if you have a total energy of 1 joule, if you started off with an energy of 1 joule, each stair, the height of each stair is 34 orders of magnitude smaller than the total energy. So you have to divide this curve into 10 raised to the power 34 small stairs. And of course, this is not perceptible. You can't see this in real world. Because h is such a small number, that is why quantum mechanics does not reveal itself so easily. You really have to go to very large frequencies, or you really have to go to the level of h to start talking to it. ठीक है, एक मशहूर कहानी हम बचपन में पढ़ते थे, गुलिवर्स ट्रैवल्स, ठीक है, जिसमें एक बहुत बड़ा देव होता था और वो ऐसी जगह जाता था, लिलीपुट जगह का नाम था, तो वहां पे छोटे छोटे बोने थे, ठीक है। अब हम एक गुलिवर है जो एक बहुत बड़े देव की तरह है, लेकिन जो क्वांटम वर्ल्ड है वो छोटे छोटे ये बोने। लेकिन अगर हम अपना साइज कंप्रेस कर दें और बिल्कुल उन बोनों के कद के बराबर हो जाए, देन वी कैन स्टार्ट टॉकिंग टू दोज पिगमीज। तो क्वांटम वर्ल्ड भी इट्स everything is quantum, but when we enter the classical world, the value of h is so small that we are really looking at an average behavior, or we are really looking at things appear to be continuous and classic, but really if you go to the level of atoms, we are able to decipher this quantization of energy. जी स्टेयरकेस में देखें, हम अगले जो 3-4 लेक्चर्स हैं इसकी ऑब्जर्वेशन पर ही बात करेंगे कि प्लैंक ने भी कह दिया एनर्जी इज क्वांटाइज्ड। अब उसकी हम एक कोरोलरी देखते हैं, till a large number of effects that show that the energy is quantized, and we're going to study one of these effects today. ठीक है, so this is Planck's idea that energy has to be quantized. But there is one inconsistency in Planck's work. Planck के काम में एक inconsistency है। अच्छा, पहली बात तो ये देखें, you have these experimental curves of energy density versus frequency, and you have a formula. C is known, C की value is known, F is known because the experiment is able to measure F with the help of a monochromator. The temperature is known, Boltzmann constant is known. So you can do a curve fitting to find the value of h. You can do a curve fitting to find the value of h. Curve fitting याद है ना सबको? You can perform curve fitting to find the value of h. So Planck also derived the value of h, and he found it to be a very small number of this order. It's a very small number. 10⁻⁻34 है। तो really quantum effects को देखने के लिए आपको बहुत small scale पे जाना पड़ेगा या हाई एनर्जीज पे जाना पड़ेगा। इसीलिए जो स्विट्जरलैंड में एक्सपेरिमेंट हो रहा है LHC, इट्स रियली वर्किंग एट दिस प्लैंक स्केल, एट दिस प्लैंक लेंथ स्केल, प्लैंक्स कांस्टेंट के स्केल पे काम कर रहा है, इसलिए वो बहुत हाई एनर्जी पे काम कर रहा है, क्योंकि तभी क्वांटम इफेक्ट्स अपीयर होंगे। ठीक है, अच्छा, अब प्लैंक के काम में एक इनकंसिस्टेंसी थी। And what was the inconsistency? If you look at the cavity again, the cavity has walls, and Planck said that there are atoms inside the walls which are quantized. But all the derivations that we've done for the classical wave theory, and if we derive the density of modes, that was based on standing waves. Okay, that was based on standing waves. So this is a standing wave, whereas the atoms are quantized, and there is an inconsistency. Einstein entered the picture in 1905. और आइंस्टाइन ने 1905 में 3 पेपर्स लिखे। एनालिन दैट फिजिक, जर्मन एक था बहुत मशहूर मैगजीन, उसके अंदर 3 आर्टिकल्स लिखे। एक आर्टिकल उसने लिखा रिलेटिविटी पर, ऑन द इलेक्ट्रोडायनामिक्स ऑफ मूविंग बॉडीज के नाम से रिलेटिविटी पर आर्टिकल, स्पेशल रिलेटिविटी पर लिखा। एक आर्टिकल उसने लिखा ब्राउनियन मोशन पर। और अगर आप एक्सपेरिमेंटल फिजिक्स की लेबोरेटरी नंबर 2 करें तो यू हैव एन एक्सपेरिमेंट ऑन ब्राउनियन मोशन व्हिच लुक्स एट आइंस्टाइन्स वर्क। एंड द थर्ड पेपर दैट ही रोट वाज ऑन द photoelectric effect. And I've already mentioned that 1905 is called the miraculous year of physics, the annus mirabilis of physics, the miraculous year of physics, because of these 3 papers. Each one of them was worthy of a Nobel Prize. Each one of them was worthy of a Nobel Prize. But when the Swedish Royal Academy conferred upon Einstein the Nobel Prize in 1922, it was because of the photoelectric effect. And this is something we're going to study. So Einstein used Planck's work. Einstein used Planck's work and removed certain inconsistencies and went a leap ahead of Planck. देखो, साइंस की जब आप हिस्ट्री पढ़ते हैं, साइंस की हिस्ट्री में आपको ऐसे लोग नहीं मिलते, बहुत कम ऐसा होता है कि there is a solitary worker. He is a solitary worker, he does not talk to people, he does not read the literature, and he makes an invention or a discovery that can change the course of human civilization. Giants stand on the shoulder of giants. एक साइंटिस्ट अपने से पिछले गुजरने वाले साइंटिस्ट का काम इस्तेमाल करता है। प्लैंक ने इस्तेमाल किया, मैक्सवेल ने इस्तेमाल किया, हर्ट्ज ने इस्तेमाल किया और आइंस्टाइन ने इस्तेमाल किया। And all of these papers are based on statistical mechanics, heat and thermodynamics, and basic electrodynamics, the Maxwell's equations, which you've already studied. So Einstein used the literature that he had available. न्यूटन ने भी इसी तरह किया था। न्यूटन ने कोपर्निकस का काम इस्तेमाल किया था, जोहानस केपलर का, टाइको ब्राहे का काम इस्तेमाल किया था। कोपर्निकस ने अरब साइंटिस्ट्स का काम, अरब एस्ट्रोनॉमर्स का काम इस्तेमाल किया था। अरब्स ने ग्रीक्स का इस्तेमाल किया था, ग्रीक्स ने चाइनीज का इस्तेमाल किया था, जो नॉर्थ अफ्रीकन्स का इस्तेमाल किया था, बेबीलोनियंस का काम इस्तेमाल किया था। So this is how human civilization progresses. Now Einstein had a whole body of literature in front of him, and he removed certain inconsistencies in Planck's work, and he made the imaginative leap that not only are the atoms quantized, the atoms are particles. हमें पता है कि atoms particles हैं, ठीक है? Atoms are discrete units. Matter is not continuous. Faraday के वक्त से ये पता है, electrolysis के experiments में आपको बताऊंगा. So the atoms are quantized, they are discrete units. But Einstein said that even the radiation is quantized. So the Einstein's picture of this experiment is that you have a cavity. The atoms, of course, they are quantized, and the energies of the atoms are quantized. But inside the cavity we have radiation. And the radiation, he thought of the radiation as comprising a large number of particles instead of waves. आपको गैस का पता है क्या होता है? गैस क्या होता है? मॉलिक्यूल्स हैं, and the molecules, there is no intermolecular forces. The molecules are independent units moving inside the cavity. That's what happens in a gas. So Einstein presented the idea that radiation is in fact a gas of particles. It's like a gas of particles, and those particles he called photons. So radiation is in fact a photon gas. And when inside the cavity an oscillator has an energy NHF, when it makes a transition, that is, if the oscillator is in this state, it's in a quantized state, and it jumps down to a lower state, when it makes this transition on the energy ladder, energy has to be conserved. The energy of the atom goes down, but a particle is emitted. A photon is emitted. A photon is emitted, and the energy of the photon is equal to the difference in these energy levels. And the difference we know is HF between adjacent levels. If it makes a transition from n equals 2 to n equals 0, one photon is emitted with energy 2HF. So there is a gas of photons inside the cavity, and they have energies NHF. Okay? N will also be an integer because the atomic energy levels are quantized, and so the photons have discrete energies 0, HF. A photon cannot have energy 0, sorry, HF, 2HF, 3HF, 4HF, and so on. So this is Einstein's idea, that the atoms are quantized. We already know that their energies are quantized. Planck showed this. But inside the cavity there is radiation, and instead of looking at the radiation as waves, let's look at the radiation as particles or photons, and they have discrete energies HF, 2HF, 3HF, and so on. A photon cannot have energy 0 because it doesn't exist. I'll let you know, it doesn't have a rest mass. Okay? So this is Einstein's picture of quantization. Radiation is also quantized. Matter is quantized, radiation is quantized. और matter और radiation दोनों मिल के यूनिवर्स बनाते हैं. यूनिवर्स में यही दो चीजें हैं, मैटर और रेडिएशन. फिजिकल यूनिवर्स में मैं बात कर रहा हूँ, ये दो चीजें हैं, मैटर और रेडिएशन, और ये दोनों चीजें मिलके यूनिवर्स बनाते हैं. And both of them are quantized. So this is the quantum theory. Now how do we show that quantum, we really need a large number of experiments to show that this radiation is quantized. And the first experiment that Einstein explained, Einstein was not an experimentalist. वो एक क्लर्क था जो एक पेटेंट ऑफिस में काम करता था, और उसके पास पेटेंट्स के डॉक्यूमेंट्स आते थे. स्विट्जरलैंड में था, पेटेंट्स के डॉक्यूमेंट्स आते थे, और वो क्लरिकल काम करता था, उसकी पैटर्न्स को इवैल्यूएट करता था. बट ही डिड नॉट परफॉर्म एक्सपेरिमेंट्स ऑन हिज ओन. ही वर्कड on experimental results produced by other scientists. In this case, he worked on the results produced by Hertz. Hertz ने photoelectric experiments पे काम शुरू किया. फिर 1896 ही में आपको पता है इलेक्ट्रॉन डिस्कवर हुआ. देखो हिस्टोरिकल प्रोग्रेशन ज़हन में रखें तो बड़ा अच्छा लगता है. 1896 में जे थॉम्सन ने इलेक्ट्रॉन्स डिस्कवर किए अपनी कैथोड रे एक्सपेरिमेंट्स में. At the turn of the 20th century, जब 20th century अंगड़ाई ले रही थी, तो बहुत से काम हुए. हर्ट्ज ने इलेक्ट्रोमैग्नेटिक वेव्स, रेडियो वेव्स प्रोड्यूस की. ये प्लैंक ने 1896 में अपना फॉर्मूला पेश कर दिया. 1896 ही में जे थॉम्सन ने कैथोड रेज डिस्कवर की. उसने बताया कि इलेक्ट्रॉन्स आर पार्टिकल्स, so we are moving from waves to particles. अब आइंस्टाइन ने भी ये आइडिया पेश कर दिया कि these photons are in fact particles and radiation comprises photons. लेकिन एक प्रॉब्लम है कि if you talk about a particle, and we know that light has a frequency and light has a wavelength, so but these are wave concepts. When you talk about wavelength, it's a wave concept, but Einstein said that light is a particle. So how do we reconcile the two concepts? And next week we're going to study the wave-particle duality. But let's talk about the photoelectric effect now. And this is the first direct experimental evidence that photons exist or radiation is quantized. the experimental arrangement for the photoelectric effect. Alright, so there is an evacuated glass bulb. Vacuum technology had already developed a glass bulb which was evacuated and a cathode. This was a certain alkali metal, for example sodium, potassium. Remember, alkali metals are very sensitive to air, they are oxidized instantly. And potassium reacts with water and sodium, both of them react with water violently to give you an alkali. They're alkali, that's why they're alkali metals. So these are really very difficult experiments. You cannot expose your tube to air or water or moisture. And if you want to make an anode of a particular shape, you have to work on a lathe machine. But these are very soft metals, very difficult to machine these metals. So remember the skill of the technicians and the scientists which goes into making such an experiment. It looks easy on paper, but these are very difficult experiments, remember. And we're talking about 110 years ago. So this is a particular metal, this is another metal, this is a microammeter which can detect any current through the circuit, and this is a voltage divider. When light falls on the metal, electrons are ejected. Okay? When light falls on the metal, electrons are ejected from the metal. And this ejection of electrons upon illumination of light is called the photoelectric effect. Photons come in or light comes in and it gives you electricity. This is how solar cell works. So electrons are ejected from this surface, they go into the vacuum, and if there is a potential, if there is a positive potential here, they will be attracted towards the positive potential and they will make up a current. Now, a few important things which classical theory cannot explain. The first thing is that if the intensity of the light goes up, okay, let me first. अच्छा, अब देखिए जरा ध्यान से बात सुनिए। इस एक्सिस पर अप्लाइड वोल्टेज है, इस एक्सिस पर ये करंट है, ठीक है। अब दिस इज जीरो वोल्टेज एंड इफ वोल्टेज इज पॉजिटिव it means let's call this A, this electrode A, and this electrode is B. Voltage positive means B is positive. ठीक है, this is positive. And voltage negative means B is negative. That is, this is negatively charged. This plate is negatively charged. You can change the direction of the battery to make this an anode or a cathode. And here is the photocurrent. The current produced by the electrons and is measured by this microammeter or galvanometer. Okay? And if you plot this, the experimental curve looks like this. When the voltage is negative, that is when this is negatively charged, even then there is some current flowing through the circuit. But at a certain voltage, when this voltage is negative enough, all the current stops. Okay. Intensity W1. So this curve is obtained when the intensity of the incident radiation is W1. Everything is clear up to so far? Now let's repeat the experiment with a different intensity of light, with a higher intensity of light, that is, more light is falling onto this electrode. If you repeat the experiment with a larger intensity, W2, which is larger than W1, this is the curve you get. The curve, the zero current value coincides, the voltage for the zero current coincides, the maximum photoelectronic current goes up with the intensity. So these are the experimental curves. Now how do we explain these experimental curves, and how does classical theory fail? Now why do we get this behavior? That is, even when this electrode is negatively charged, why do we get any photocurrent at all? Okay, let me ask people from the back. पहले तो ये बताएं कि intuitively, if this is negatively charged, if you make this electrode more and more negatively charged, should the electronic current go up or down? At the back, it should go down, because now this electrode is repelling the electrons. But why for negative in this region, when the voltage is negative, why is there any current at all? Current आखिर है ही क्यों? कोई और बताओ, आप बताएं। आपको मेरा सवाल समझ आया? अब उसका जवाब है ज़हन में आपको? चलिए आप बताएं। बिल्कुल बिल्कुल। अब देखो, this is a repulsive force on the electrons. The electric force, the electrons have to move against the electric field, because this is negatively charged. The electrons are negative electrons are trying to move towards a negatively charged plate, and they have to overcome some force, and they can only overcome this force if they have sufficient kinetic energy. So the electrons ejected from this surface have some kinetic energy, and because of that kinetic energy, they can overcome the repulsive force from this electrode, from the electrodes. And when they have enough energy, they can still fall on B despite B being negatively charged and make up a current. But the current eventually stops. And the current stops when V0 reaches a certain value. That is when the barrier or the electric force which is resisting the motion of electrons is so strong that no electron has enough kinetic energy to make up a current. So this is really a measure of the maximum kinetic energy of the electrons. This is really a measure of the maximum kinetic energy of the electrons, V naught. So if I write K max, the maximum kinetic energy of the electrons which are ejected from the surface. देखो electrons की एक energy नहीं होगी, there will be a range of energies of electrons, but there will be maximum kinetic energy. And if I write K max equals half m V max squared, what should this be equal to? If that V naught, if you know what V naught is, ये काइनेटिक एनर्जी किसके बराबर होगी? अब मैं आप सवाल पूछ रहा हूं, आप बोलिएगा ना, आप बताइए। ग्रीन शर्ट में, ग्रीन टी शर्ट में जी, आप आपके साथ जो बैठे, आप बताइए।
तो मुझे क्वेश्चन समझ नहीं आया था, V नॉट कह रहे हैं, B नॉट कह रहे हैं?
ये मैक्सिमम काइनेटिक एनर्जी किसके बराबर होगी?
हाफ एम वी स्क्वायर।
हाफ एम वी स्क्वायर, और हाफ एम वी स्क्वायर किसके बराबर है? आप बताएं, साथ बैठे नहीं आप। If V naught is the potential at which the current drops to zero, what is the maximum kinetic energy equal to? Very simple question. आपको सवाल समझ आया? आप बैठी हुई हैं साथ जो?
जी जी सर।
Can you answer me? You understand the question?
Yes yes I understand.
आप बताएं, ब्लू शर्ट में।
EV नॉट।
बिल्कुल, it's going to be equal to EV naught. Very simple. So V naught is called the stopping potential. This is the potential at which no electron is sufficiently energized enough to constitute a current. V naught E will give you the maximum kinetic energy. But if you look at these curves, if I increase the intensity of the light falling onto this metal, okay, classically we know that the intensity is proportional to the square of the electric field. For an electromagnetic wave, the intensity is proportional to the square of the electromagnetic field. And this gives you the intensity. So we are putting, classically we tend to think that we are putting up more energy, we are throwing more energy onto this electrode. We are throwing more energy onto this electrode, the maximum kinetic energy of the emitted electrons must go up. ठीक है, अगर हम ज्यादा एनर्जी एक मेटल सरफेस पर फेंकें, because we have increased the intensity, we are giving more energy to the electrons inside the metal, and when they are ejected, they must have a higher maximum kinetic energy. But when we look at this curve, we increase the intensity, the current increases, the current does increase, but the maximum kinetic energy remains the same, because the same voltage can stop or halt the photo current completely. ये वोल्टेज पिंच कर रही है करंट को, वोल्टेज रोक रही है करंट को, वही वोल्टेज जो पहले करंट को रोक रही थी अब उतनी ही वोल्टेज करंट को रोक रही है। इसका मतलब कि मैक्सिमम काइनेटिक एनर्जी हैज नॉट चेंज्ड. So even though we are putting up more energy onto this plate, the maximum kinetic energy of the ejected electrons remains the same. So this is one problem with the classical theory. We are putting up more energy, we expect the kinetic energy of the ejected electrons to go up, and therefore we expect the stopping potential to be more negative, but the stopping potential is still the same. So this is one problem with the classical description. All right. The other thing I would like to mention is the following. एक मिनट. Okay, I'll answer your question in a minute. The other experiment that was performed with the same setup is that now you vary the frequency of the light. ठीक है, जो लाइट उसके ऊपर गिर रही है, vary the frequency of the light. Now how do we vary frequency of a light? We use lights of different colors. We can filter, we can use a different color light source. That's how we need to use a different light source or be able to filter the frequency of interest. Alright, so vary the frequency of the light and keep W constant. That is, keep the intensity of the light the same. ठीक है, 5 वॉट का बल्ब है, 5 वॉट का लाइट सोर्स है, 5 वॉट का लाइट सोर्स यूज करें, लेकिन फ्रीक्वेंसी डिफरेंट, कलर डिफरेंट. अभी लेजर्स डिस्कवर नहीं हुए, लेजर्स इन्वेंट नहीं हुए, 1960 में लेजर्स हुए. सो वन हैड टू यूज xenon lamps or neon lamps or mercury bulbs with different filters. So keeping the intensity of the light constant, if you change the frequency, a very interesting behavior is observed. And the behavior is that increasing the frequency increases the stopping voltage required. This means that if we increase the frequency, the maximum kinetic energy of the ejected electrons is increasing. ये V naught stop negative potential का ये magnitude है. ठीक है, the V naught is negative. Now we are applying a negative voltage, and if we increase the frequency, which means on this curve we are performing an experiment with intensity W1, but now with a higher frequency. So with the higher frequency, this curve goes like this. So this is intensity W1, higher frequency of light. So with this higher frequency of light, a higher stopping potential is required, which means that the ejected electrons have now become more energetic. But the intensity has not changed. So now we have not changed the intensity of light. Light that is falling on the metal has not changed, but we observe that the electrons which are being ejected from the metal surface, they are more energetic. Where is their energy coming from? We haven't increased the intensity of light falling onto the metal, which means classically we haven't increased the energy. But where is that extra energy coming from? Okay? So this cannot be explained classically. ठीक है, इसको एक्स्ट्रापोलेट भी कर सकते हैं आप. जी बिल्कुल यही बात है. देखो ये दो ऑब्जर्वेशंस समझ आ गई, और क्लासिकल कॉन्सेप्ट का फेलियर भी आपको पता चल गया होगा कि यू आर इंक्रीजिंग द इंसिडेंट इंटेंसिटी, यू आर इंक्रीजिंग द लाइट दैट इज फॉलिंग ऑन टू द मेटल, बट द एवरेज काइनेटिक एनर्जी ऑफ द इलेक्ट्रॉन्स इज नॉट गोइंग अप. The average kinetic energy of the electrons, however, is going up when you are increasing the frequency of the light. These are two observations that cannot be explained classically, and it was Einstein who explained them correctly. The third thing that cannot be explained classically is, you have to read it on your own in the book, is that photoelectric effect is instantaneous. Light fall हुई, immediately a photocurrent starts flowing. Classically, you would say that light is falling, energy is falling onto the metal, the energy of the electrons inside the metal must gradually go up till they have enough energy to break away from the metal surface. But photoelectric effect is an instantaneous effect. Now how do we explain all of these observations? We explain these observations by saying that light comprises photons. Light is photons. It's a very strange sentence because this is a singular and this is a plural. ये जमा है वाहिद, यानी अजीब सा सेंटेंस लग रहा है, light is photons, but still it's true. And a photon has a certain energy, and the energy of the photon is hf. A single photon carries an energy hf, and when this photon, if you draw the metal surface, this is the metal, and inside the metals there are positively charged nuclei and cores, ठीक है, and there is a sea of electrons. ये आपको पता है ना, sea of electrons है, इसके अंदर बहुत से electrons हैं जो बिला खौफो खतर घूम रहे हैं अपनी मर्जी से, ठीक है, उनको आने जाने की कोई रोक टोक नहीं है ज़्यादा, ठीक है. There is a sea of electrons, the soup of electrons. Now when light falls onto this metal, and light basically comprises a photons. So a single photon, consider a single photon falling onto the metal. The photon has a frequency f and an energy hf. It comes in contact with the metal, and if the photon has sufficient energy, it can eject the electron from the metal. It can knock off the electron from the metal. ठीक है, इतनी सफिशिएंट एनर्जी होनी चाहिए कि वो इलेक्ट्रॉन मेटल से बाहर निकाल दे, वैक्यूम में फेंक दे इलेक्ट्रॉन को, मेटल से वैक्यूम में फेंक दे. यानी इस फोटोन के अंदर इतनी एनर्जी होनी चाहिए कि वो अट्रैक्टिव फोर्सेस इन आयरन कोर्स की इलेक्ट्रॉन की तरफ उनको ओवरकम कर सके. इट मस्ट इम्पार्ट एनफ एनर्जी टू द इलेक्ट्रॉन दैट द इलेक्ट्रॉन इज एबल टू बी इजेक्टेड. And when the electron is ejected, it will possess a certain kinetic energy. ठीक है, उसकी एक kinetic energy होगी इस ejected electron की. So ये जो photon है, जब electron को eject कर देगा, it will disappear in the process. ठीक है, वो कुर्बानी दे देगा photon, वो गायब हो जाएगा. It will be absorbed. वो खुद जल जाएगा, लेकिन इसका दरख्त है वो धूप में जलता है, लेकिन नीचे मुसाफिर को साया दे देता है. तो ये इलेक्ट्रॉन, ये जो इंसिडेंट फोटोन है, इट विल बी अब्सॉर्ब्ड, इट विल डिसअपीयर इन द प्रोसेस, बट इट विल क्रिएट एन इलेक्ट्रॉन एंड द इलेक्ट्रॉन विल कम आउट ऑफ द मेटल सरफेस. ठीक है, एंड द इलेक्ट्रॉन विल हैव काइनेटिक एनर्जी आफ्टर इट हैज कम आउट ऑफ द सरफेस. So where is the energy of the photon going? The energy has to be conserved. Some of the energy is going in, let's call it phi. Some of the energy is going in overcoming the attractive potential of the electron. And this energy is called the work function of the metal. ठीक है, इस एनर्जी को वर्क फंक्शन कहते हैं. हर मेटल का एक वर्क फंक्शन होता है. मसलन पोटेशियम का वर्क फंक्शन विल बी अबाउट 2 इलेक्ट्रॉन वोल्ट्स. इतनी एनर्जी चाहिए मिनिमम फोटोन को पोटेशियम मेटल में से इलेक्ट्रॉन को इजेक्ट करने के लिए. अगर फोटोन की एनर्जी इस वर्क फंक्शन से कम होगी तो इलेक्ट्रॉन विल नॉट बी इजेक्टेड. एंड एनी एक्स्ट्रा एनर्जी दैट दिस फोटोन possesses goes as the kinetic energy of the electron, and energy is conserved. So this is the photoelectric equation. Since these are the last 5 minutes, I will answer questions after the lecture, but let me explain this. So this is the photoelectric equation. We can explain all our experimental results based upon this model. But remember, what does this model assume? The photon is a particle. It possesses an energy hf. It collides with the electron, which is a particle. It gives energy to the electron. If enough energy has been given to the electron that it overcomes the work function, the electron will be ejected from the metal surface and it will be free. It will be free inside the vacuum tube. And it will possess kinetic energy. So now let's first explain this curve. If you look at this curve, a minimum frequency is required. You see, V naught is kinetic energy maximum over E. ठीक है ना, ये आप एग्री करते हैं ना? A minimum frequency is required. If F is at this value, F naught, if F is equal to F naught, the maximum kinetic energy is 0. ठीक है? So what is F naught equal to? If you look at this equation, HF naught is equal to the work function. So the photoelectric effect equation is in fact HF equals HF naught plus the kinetic energy of the emitted electron. याद रखें यहाँ पे maximum kinetic energy नहीं, एक kinetic energy of the electron इस equation में. तो frequencies have to be above a certain threshold value. Frequencies have to be above a certain threshold value for the photoelectric effect to take place. If you increase the intensity of radiation, अच्छा, sorry, एक बात पहले मैं आपको बता दूं, अब frequency इस threshold value से ज्यादा होनी चाहिए, क्योंकि इस threshold value पे HF naught, which is the photon energy, equals the work function. This is the minimum energy that is required for the photoelectric effect. And if F goes beyond F naught, the electrons will have some kinetic energy, and the maximum kinetic energy will go up. Which means that it is not the intensity of the radiation, but HF, which is really a measure of the photon energy. Now what happens if we have photons with frequencies less than F naught? No photoelectric effect can take place, because you have not overcome the work function. Even if you shine more light onto the metal plate, that is, you increase the intensity of the radiation, you're just increasing the number of photons. You're not changing the frequency. So in the quantum picture, intensity is W is really proportional to the number of photons. But each photon has the same frequency F, because you're not changing the color, you're just shining more photons onto it. You're giving it more photons, but each photon doesn't have enough energy to eject the electron. तो ये इसी तरह की बात है कि आप किसी अहमक शख्स को बात समझाने की कोशिश करें और आप उसे फलसफा और दलीलें और हिकमत के अक़वाल सुनाते हैं, पर वो समझे ना. You're increasing the amount of information to him, but he's not responding. You're increasing the intensity of light, which means that you're increasing the number of photons. So this picture of light falling onto the metal plate is really a large number of photons that are falling onto the metal plate. And if you increase the number of photons, but they don't have sufficient energy or sufficient frequency, no photoelectric effect will take place. That is why we have these two curves, but each one of these curves has the same stopping potential. Okay? Which means they have the same maximum kinetic energy. Okay? However, if you increase the number of photons, what is current? Current का क्या मतलब है? Number of charges per unit time. If you increase the number of photons, keeping the frequency the same, the stopping potential does not change, which means the maximum kinetic energy does not change, but the number of electrons flowing through the circuit goes up, because each photon is now producing a photoelectric effect. ठीक है? हर फोटोन फोटोइलेक्ट्रिक इफेक्ट प्रोड्यूस कर रहा है. याद रखें, क्वांटम प्रोसेस में ये फोटोइलेक्ट्रिक इफेक्ट टेक्स प्लेस ऑन एन इंडिविजुअल बेसिस. One photon interacts with one electron, produces the photoelectric effect. Another photon interacts with another electron. So more the number of photons, the more the number of electrons will be ejected, but their energy will not increase. Only the number will increase. And since the number of electrons flowing through the circuit per unit time has increased, the photocurrent increases, and that is what we observe here. So if you look at this curve, from a slope of this curve, when the maximum kinetic energy is 0, you can find the value of frequency. You can analyze this curve, and from the slope of this curve, you can find the value of h as well. So this you should do as a homework. So in summary, what we've seen is that the photoelectric effect can only be explained on the basis that light comprises photons and they interact on a one-to-one basis with the atoms. So in our next lecture, we look at another experiment which shows that radiation actually comprises photons. Thanks a lot. Questions at the end?